Teams. Okay.
Okay, Flavio, you can go.
So thank you, Jill, for your introduction. I will talk to you today about the LS simulations of wind turbines in a turbulent atmospheric boundary layer. So I work at HLRS, the High Performance Computing Center of the University of Stuttgart. My name is Flavio Galeazzo, and I work in a team together with Andreas Hupp and Ralf Schneider. So I will begin my presentation with a short introduction. Then I will talk about the simulation approach, about the turbulent atmospheric boundary layer and the wind turbine simulation, a bit about the codes that I use to do the simulations, the benchmark. I use it to compare the results, then the results, and I will end with a conclusion and the next steps. Okay. The main objective of this of my work in HPCWE is to perform a VVUK study. That is the verification, validation, and uncertainty quantification. Especially of the integration of meso and microscale simulations. For example, it's the weather scale to wind turbine scale. But before I can move to this to the full study, we have to separate this framework. So first, I will show you the verification. The verification answers the questions if the answer the question that if the equations are being solved correctly by the software that we are using. Then after that, we'd go to the validation. If we are using the right model and equations for the applications we are using. And at the end, the uncertainty quantification to determine the probability distribution of the outputs given an uncertainty in the input factors. In the first years of the project, the focus was on the verification and validation parts of the study, preparing the framework for the uncertainty quantification. The simulation approach that we are using have the focus on the interaction of wind turbines in wind park. That's similar to what Richard Stevens has already presented us right before my presentation. For that, I will use the same approach as Stevens. This is the large eddy simulation. With this kind of simulation, we can predict the wake of wind turbines with high fidelity. We can resolve the large turbulent structures, but it requires large computational time. Then we have to use HPC, high performance computing, for that. The simulation approach for the turbulent atmospheric boundary layer that I'm using, it's a mean velocity profile that's given by a logarithmic function. That's pretty standard for the boundary layer. But for the LS simulation, we need to add turbulent structures, turbulent fluctuations on top of this mean velocity profile. For that, I have used two different approaches. One approach is using a precursor simulation. That's similar to the method described by Stevens. The results of a simulation without the wind turbines is stored and used as inflow condition. We see at the right-hand side animation of this, the development of this boundary layer and also the development of these turbulent structures. They have the good side is that they can represent very good the turbulence in this boundary layer, but it needs more computational time. So it consumes a lot of computational resources, and it's also difficult to match experimental values using the this precursor simulation because you don't have much possibility to control the turbulence intensity. Another way to create these large-scale turbulent structures is using synthetic turbulence. We are seeing the animation at the right-hand side. I start with the laminar flow, and then you see these turbulent structures being convected through the computational domain. The synthetic turbulence approach, it saves computational time in comparison to the precursor simulation. It also allows finer adjustment of the desired quantities of the turbulent flow that we want to simulate, but it's not readily available in our codes. In this case, these results I'm showing using the synthetic turbulence have been done using OpenFOAM. The simulation approach for the wind turbine is the actuator line model. Professor Stevens has already explained it in more detail in the last presentation. In this model, we divide the turbulent blade into smaller elements and retrieve these forces exerted by the turbine on the flow from 2D airfoil data. With this approach, we can model non-uniform velocity and load distributions in the wind turbine. I have used two different codes to run the simulations. One is Wink3D. That's the wind farm version of Incompact 3D. That's both are open source codes developed by our project partner Imperial College London. Wink3D uses a finite difference method with sixth order discretization in space. It shows a very good scalability. It has been shown to scale well up to 100,000 ranks. It has an actuator line model implemented, and we can use Wink3D to simulate neutral atmospheric boundary layer. The other code that I have used is OpenFOAM with the turbines FOAM module. Both are also open source. In this case, used a finite volume method with second order discretization in time and space. OpenFOAM is shown to scale well up to 5,000 ranks, maybe a bit more, but it doesn't scale so well as Wink3D. We have more options in OpenFOAM. We can use actuator line models or also actuator disk. And we can also use OpenFOAM to simulate neutral, stable, and also unstable boundary layers. For the benchmark, so to compare the simulations, I have used the experimental data from the SWIFT benchmark. The SWIFT benchmark is part of the International Energy Agency Wind Task 31. That's in this case operated by Sandia National Laboratories. The measurements have been the wind turbines are installed in a flat terrain. They have 3 variable speed, variable pitch modified Vestas wind turbine generators. They have a meteorological tower that collects the free stream or the wind velocity. They have also a rear-facing nacelle-mounted LiDAR to measure the wake velocity of produced by the wind turbine, and also power and loads measurements that are collected and available at this website. In this SWIFT benchmark, they have measurements of neutral, stable, and unstable atmospheres. I have used the neutral ABL for the validation of the simulations. They have high frequency measurements of the inflow conditions and also the turbine operations in 10-minute periods. So on each 10-minute period selected for this benchmark is referred to an ensemble, and they have 6 different ensembles for this neutral ABL. At the right-hand side, we have the parameters of this neutral ABL. The wind velocity at hub height is 8.7 meter per second, approximately 10% turbulence intensity. And here we have the parameters for the logarithmic profile. Now I'm moving to the results. I will begin first with the verification of the code. The verification step is one where we see if the implementation in the code is represents what the modeling paper predicted. And when I took the Wink3D code, I found 2 inconsistencies. The first one is an inconsistency related to how the blade elements are computed from the input data. This error is relevant as it implies not using the full length of the blade. If you don't correct it, the input data is represented here by the red. Sorry. It's represented by this red curve, and the originally computed by the Wink3D, they have used a shorter. They have used the points, the blade element points, as end and as first and last element of the blade, which is not correct. So also I found a bug in the random noise generator that is used to trigger the turbulence in the precursor simulation. The original code had a bias toward positive values of the horizontal velocity component that caused some inconsistency in the results. Both bugs have been corrected, and the publishing of these results are ongoing. I have already contacted the colleagues in the Imperial College. For the open form with the turbines form module, I found a similar inconsistency as Wink3D related to how the blade elements are computed from the input data. It's very similar, the issue. And the corrected code has been already published and is available at the turbines form GitHub repository. A bit more specific about the simulation setup for this for the simulation using both codes. For the Wink3D, the simulation type is LAS. For the OpenFOAM 2, for the Wink3D, I have used SGS Smagorinsky as SGS model, supergrid scale model. For the OpenFOAM, I have used Whale. The discretization methods are different. So Wink3D uses a finite difference method, while OpenFOAM uses a finite volume method. The grid type is also different. Wink3D uses a structured and OpenFOAM an unstructured grid. Wink3D is high order code with 6th order discretization in space and 3rd order in time, while OpenFOAM remains with 2nd order in space and time. And both models use a actuator line model for the wind turbine. The validation, the numerical domain that I have used is 270 to 540 meters. The rotor diameter of the wind turbines is 27 meters. The grid spacing is 2, which gives approximately 30 elements per rotor diameter. It's a rough grid that's I chose this because when we want to simulate the large wind farms, we want to have a course. We don't want to have a very fine grid. In this computational domain, I have around 5 million hexagonal elements. The time step is 0.05 seconds for both codes, and the simulation times of 10 minutes as in the measurements. Now I'm showing results of the vertical profiles. Here, a vertical profile that's 2.5 diameters before the wind turbine as the measurements are. We see here profiles for the mean wind velocity, or mean, and the turbulent kinetic energy, TKA. And we see that the mean velocity shows good agreement with both simulations when we compare with the black lines here that are extracted from the experiments. But we see that both simulations underestimate the turbulent kinetic energy. Here we see the profiles for the generator power over time. Here's the time axis, and here the generator power. And at the right-hand side, we have the mean value of the generator power, and in black, the black lines are the standard deviation. We see that the mean power is overpredicted by both codes, Wink3D and now OpenFOAM. By Wink3D, we have plus 9% mean power. By OpenFOAM, much more, 20 plus 27%. While the standard deviation, the standard deviations are underpredicted by both codes, by both Wink3D and OpenFOAM, which corroborates with the underpredicted TKA. So, exploring the possible causes, one possible cause is that the mean velocity changed considerably in the 10 minutes interval. Here we have the time axis, here the inflow velocity, wind velocity. In green, the measurements. We see that we have changes that are not only related to turbulence, they have it's larger structures than the turbulence that is being modeled. And in blue, we have the OpenFOAM simulation that had a mean velocity with the turbulence structures superimposed. So the solution for that is was to implement a variable velocity inflow condition based on a moving average of the experimental data. Now we have here in blue, the mean velocity was superimposed with the turbulent structures, but it follows this path, this mean velocity profile from the measurements. It had a good impact in the TKA. We are seeing now the same mean velocity profile and TKA profile, but using now this OpenFOAM simulation using the variable mean velocity inflow condition, but using the same parameters for the synthetic turbulence as the previous simulation. We see that the mean velocity, the mean velocity profile remain in good agreement here. But the TKA is in much better agreement with experimental data than before, even though the synthetic turbulence has the same parameters. We see that the observed fluctuations are not only turbulence in nature. And the TKA here, turbulent kinetic energy, may be an appropriate nomenclature for this value that has been calculated, because it's not related only to the turbulence. It also has a variation of the mean velocity profile. Naturally, the varying mean flow velocity also affects the power output and the rotor speed of the wind turbine. Here we have the results using the constant mean velocity for velocity, power, predicted power, and the rotor speed using one single mean velocity and using the variable mean velocity. Then we see that although not perfect, the agreement is better using this varying mean velocity input. Now a bit closer look in the generator power, a comparison with from one of the series from the uh, benchmark and the OpenFOAM simulation using the varying input mean velocity. We see that the power prediction is much better now. So the agreement is better. The difference comes from 27% over prediction using a single mean velocity down to a plus of 6% now. And the standard deviation is also a much better agreement with the experiments. Talking a bit about the HPC resources that have been used for these simulations. The simulations have been run in the Vulkan cluster here at HLRS using 2 nodes with 4 cores of Intel Xeon Gold processor. The results show that OpenFOAM utilizes fewer resources than Wing3D using this agreed with the same number of elements. OpenFOAM utilizes only 25% of the Wing3D computing time when considering precursor plus main run simulations. And considering the main run only, OpenFOAM utilizes 55% of the Wing3D computing time. The Wing3D using a different inflow condition, not this, the precursor simulation is currently being investigated in our group. Now to the conclusions. We have successfully done a verification of 2 CFD codes for the wind turbine simulation, Wing3D and OpenFOAM with turbine foam module. And code corrections have been published or are going to be published shortly. We have also successfully validated the simulations using experimental data from the Swift benchmark, and also developed a variable velocity inflow condition for OpenFOAM. The next steps is to investigate the influence of mesh refinement in the results, considering the differences of Wing3D and OpenFOAM regarding the grid generation and also the discretization order, and then proceed with the uncertainty quantification study. So thank you, and I'm glad if to answer any questions that you have.